Hello, good morning, everybody. Very welcome here to this session on which is around the FertiCovery project on best available technologies to recover or recycle fertilizing products from secondary raw materials. We are here with people from the project consortium. We are with our project officer, Stefania Rocca, and also with the head of unit, who spoke also this morning already twice. So happy to hear you here, that you're here, in Mr. Milukas. Yeah. So I would like to give the word first to our colleagues from the European Commission, and they have an introductory presentation.
Thank you, and good morning, everyone, and a very warm welcome to this session. I already introduced myself. If I'm doing more, my name is Anders Milukas. I'm head of unit Biodiversity, Circular Economy, and Environment at the European Research Executive Agency. And it's, of course, a pleasure to me to be here today and to open this FertiCovery project session. So first, I would like to start with a big thank for organizer for putting such a thoughtful program and for you being here. And of course, it's very good to have researchers, innovators, industry and policymakers in the same room. And I think we have some people joining online, even from Brussels. So that mix is exactly what makes such events very valuable. And of course, bringing everyone around the topic of bio-based fertilizers feels especially timely because a few of the topics connect so many things that we care about right now, like food security, like competitiveness of our industry, like resilience of our supply chains, as well as our commitment to the cleaner, more circular economy as this topic. So the work you do turning these secondary raw materials back into valuable products like fertilizers is right at the heart of all this. And as you know, the project is a coordination and support action. It has been funded under the Horizon Europe Cluster 6 from 2024 call under the topic dedicated to best available techniques to recover or recycle fertilizing products from secondary raw materials. And projects funded under these topics were expected to deliver a recommendation to policy makers and stakeholders on the alternative fertilizing products able to balance nitrogen and phosphorus flows within safe ecological boundaries at regional and local scale. They'll be contributing to ecosystem restorations. And projects has to contribute to deliver alternative fertilizing products with reduced environmental impacts on soil, water, and air quality, biodiversity, and climate in line with overall objectives of European Green Deal and EU Zero Pollution Action Plan. And this is really what today's meeting is about. And this session, best available techniques to recover and recycle fertilizing projects from secondary raw materials, bring the FertiCovery project and its partners together to share with stakeholders where the science and technology stands today. So over the next few hours, we'll hear the project introduce itself and walk us through the case studies it has gathered, how it shifted a long list of options down to the most promising circular fertilizing technologies, how a digital product passport can give these products the traceability and trust they need, and what a close look at the composition, the safety and the soil impact of biofertilizers can tell us. In short, a tour through what it really takes to recover nutrients and put them back to work safely and at the scale. And I would encourage you throughout the day to talk to one another, to ask questions, and to look for connection between your work and some of your neighbors. And some of the most valuable outcomes of event like these are these exchanges that start in the room and continue long after we have all gone home. So on behalf of REA, thank you again for being here. I wish you a stimulating and enjoyable session full of good exchanges, discussion and connections. So back over to speaker, and all the best for today's meeting.
Yes, please. Yeah.
Hello, good morning, and thank you also on my side for being here, participating in this FertiCovery project session. So I'm Stefania Rocca. As Martin said, I'm a project officer for this project. So actually, I'm following the implementation of different Horizon Europe projects that has been funded under Cluster 6 Horizon Europe program, which was presented extensively this morning by Arnas, which is my head of unit. And I'm very happy to be part of this project. You will hear later on the discussions, the progress that were achieved in the first part of the activities. And also we are looking forward to hear from you your feedback, to exchange ideas on best practices in the field of fertilizers. So how to go to the next slide here, I guess. So in this presentation, I will just talk mainly about three parts. So first of all, the background and the strategic initiatives, also at the policy level, behind the biofertilizer production. The second part is about Horizon Europe program. So how Horizon Europe is supporting the production of bio-based fertilizers and also the valorization of different waste streams, as also we heard this morning in the plenary. And also how to build synergies, because these are very important. So there are, you will see different parts of funded programs that are addressing these challenges, but very importantly is to build up synergies and to maximize impacts. And then finally, how our agency, the European Research Executive Agencies, is supporting projects and beneficiaries like FertiCovery, FertiTech also that will be presented today, but also other projects like yours in which you might be involved. So first of all, about the strategic picture, and I would like to add the disclaimer that I was supported by my colleagues of the Directorate General of Agriculture and Rural Development and also the Environment to set up all this overview. And so some of my colleagues might join online. So first of all, fertilizers, they are essential to agriculture productivity, but also farming and food security. And what we see in this specific evolving also moment is that 70% of European phosphate fertilizers in Europe, they are imported. Not only they are imported, but of course they are also, they cost very much, and we see also a rising cost of above 60% of fertilizers production compared the last quarter of 2025 compared to the 2020 levels. So it has an increasing cost, and we know that fertilizer production has a direct impact on food production cost, and is a major cost for farmers. So obviously it is a big, it has a high relevance for farming and the whole food production. And then it's also a high energy intensive process, and it leads to about 1.5% of EU CO2 emissions from nitrogen fixation. And also I would like to highlight that to tackle all these challenges, so to make the whole process chain more affordable, sustainable, and also competitive, there is a very recent fertilizer production plan that has been adopted by the European Commission in May 2026, so just now. So these are the figures, and what we see as well is that, of course, research and innovation, as also Arna said today, is a bridge to tackle all these challenges and also to remove, to the extent possible, the main barriers. About the strategies, so I would like here just to highlight how these very recent or new strategies are very much linked to the research and innovation supporting the EU fertilizer productions, so bio-based fertilizer production and nutrient recovery. So last year we had the EU bioeconomy strategy, also the Clean Industrial Deal. So of course these are strategies that are looking at making Europe more resilient, competitive, and also self-sufficient, and tackling also specifically the bio-based nutrients and fertilizer production. We have to look at the fertilizer products regulation, which set the rules for CE market products, and also the evaluation of this regulation. Also, there is another very important initiative, which is the revised Urban Wastewater Treatment Directive, which really pushes the recovery of nitrogen and phosphorus and also micropollutants from wastewater. So this is also something very relevant to this field of research. And then upcoming, there is the very recent in 2026, the Industrial Accelerator Act, but also the Fertilizer, as I said, Action Plan, which was just adopted in May, and upcoming Biotech Act 2, and also the upcoming Circular Economy Act, which, of course, they will also look at bio-based fertilizers and secondary resources from secondary raw materials. So all of these, of course, it is very relevant to this field of action. And then about Horizon Europe, also Arnas presented the main pillars of Cluster 6 this morning. But of course, so it is very important to highlight that many different topics, they are looking at the production of fertilizers or other resources from secondary raw materials from these different angles. But all of them, I would say they are very relevant. So, of course, it will be an opportunity for you if you are looking at how to scale up and further progress on this field of research to consider Horizon Europe Cluster 6. Also, as presented by Arnas in plenary, there is the other part of the program, which is Circular Bio-Based Europe Joint Undertaking, which is a partnership between public and private entities. And of course, this field of research is very also relevant, and there are some specific topics looking at biofertilizers. And as well, live program. One of the projects will be presented later on in the next session, and you will also hear from projects funded under the live. What we are looking at through topics funded under Horizon Europe and all this other part of the EU-funded programs is really to go from lab to more pilot scale and implementation. and also to have evidence on the performance. So we are talking about the mass, the energy balance, but also cost economics, as was also presented by Professor Fino today. So we want to see how great research ideas will go further to implementation and eventually result in concrete, real-scale solutions. And just for you to know that there are some ongoing or also closed or nearly closed examples of relevant projects funded in Horizon Europe Cluster 6. So I would just examples. I'm really sorry if I miss anything that where you will be involved. So I would like to flag the P2 Green, which is a project that is looking at circular nutrient flows, turning urban sanitary waste into fertilizers. And I would also like to encourage you to look at their final results soon in October. They will have their final event in Brussels. If I'm not wrong, it's a hybrid event, so you can follow in person or online. And yeah, so it's a great opportunity to see what has been built in the last 3-4 years in this field through the P2 Green project. There is also Walnut that has been finalized recently, and they also have very good results and recommendations also for research gaps and how to go further in certain solutions also relating to wastewater and brine. And then FertiTech, which is a so-called sister project of FertiCovery, and will be also presented later on during this session. I would like also to highlight some examples of relevant projects in the LIFE program. Here, so for example, this Zeowine, that they are looking at compost and how to improve the management, but also how to make use of the nutrients and the valuable resources that they are in this material. And for all these projects, I would like also to encourage you to look at the material available on their website or in the Commission repository database. Also, another part of projects and also good practices that you can find in this field of research is available under the European Union Common Agricultural Policy Network, which actually really connect projects, funded projects, but also operational groups that are active in the agriculture, rural development, but also fertilizer production and bio-based fertilizer production. And also here, I would like to flag the websites and also all the repository and databases where you can get, I'm sure, very valuable information. Also, this is one of my main point of today. From our perspective, we see that it is very important and key to build up synergies and collaboration opportunities among all of you. Why? So 5 main reasons. First of all, not to start from scratch, but to build up on what is already available, so avoid duplication, but also benchmark and consolidate results, identify research and innovation gap. It is also a very valuable feedback from our perspective, because this input from you will be really key in co-creating, or like maybe I should say building up the new framework program for research and innovation. So this is something that we always encourage you to share with us. And also looking at technologies that works well, so how to go to the next steps. And also important, as also FertiCovery's coordination and research and support action, it is key to convey your messages and recommendations to policymakers and also stakeholders in the field with one voice. So not only FertiCovery, but shared results as a result of collaboration that you build it upon. And as I also flagged before, there are various platforms available from where you can get valuable results and information. And for your reference, I put them here in this part of the slides. And one group that has been really recently set it up is the Bioeconomy Investment Deployment Group. It's a new platform and is also looking at funding for scale up. So if you are already at that stage, it might be also helpful for you to look at this opportunity. And then finally, how we support beneficiaries. As I said before, it is very important from us that you share robust evidence. So what works well and what doesn't work well, and where are the barriers, where are the research and innovation gaps. And this is done actually through your projects report, deliverables, but also policy briefs. And for this, actually, our agency, together with our colleagues of the Directorate General of the European Commission for Research and Innovation, but also Environment, we provided some guidance here in these publications that you can see. So to first of all share scientific evidence with policymakers. There are some useful tips and suggestions to speed up this process, but also simplify and looking really at the essential to build up these messages. And also tips for researchers, how to achieve great impact on policy, and also how to reflect about your work and its relevance for policy making. And then finally, I would conclude with some opportunities to maximize policy impact, so research, how to communicate research to policymakers and also to contribute effectively to the policymaking process. At the moment, there is an open call for evidence open until the 2nd of August, which might be relevant to the audience because it's looking at water resilience research and innovation strategy. And obviously, the recovery of nutrients such as phosphorus and nitrogen are part of the strategy to effectively use wastewaters and best manage water resources. I also included the published initiatives links. So whenever you are also doing this work, I would encourage you to look at these open opportunities. As I said before, policy briefs are a very valuable input that we will need from projects like FertiCovery and other funded projects. And finally, I would say cluster events like this or others that you might organize where you join forces with other projects. They are very important to convey major progress and results in this area. And I would like to highlight this final conference that I said before, but also SynBio projects final event in, I think it will be on a hybrid mode in December. And also contributing to policy events like and platforms like the Circular Economy Stakeholders Platform that was also mentioned by Arnas today, and the JRC Knowledge Center for Bioeconomy. And then, of course, also when we request input specifically from you, I would also very much appreciate these outcomes. Yes. And with this, I finish. So I'm happy to take any question if you have, and I will follow the whole session afterwards and stay here for also the roundtable. And I'm looking forward to exchanging with you further on this action. Thank you.
Okay, thank you very much for your overview presentation of the context of our where our project is operating in. My name is Martijn Vis. I'm from Biomass Technology Group from the Netherlands, and I'm also the coordinator of the FertiCovery project. In the next minutes, I will give you a general overview of the project and its current status, and so you have some idea. And then in the presentations hereafter, we will have some more detailed presentations on parts of our results. And also we have some external stakeholders here, so very interesting to hear also from their experiences in real practice. Well, we are running now for 18 months. We started in January 25. We just had our midterm review meeting yesterday. We have a group of scientists, like, for instance, Katif. We have the University of UNITO. We have Technical University of Athens, who also organizes this conference. So they are really the scientific experts, you could say. And of course, University of Wrocław. Oh, don't forget them. I mean, they are really, they will be impressive. They will have 3 presentations on what the interim results will be very good. 4. Oh, wow. Well, okay. They are really strong presence here. And, but we also have network organizations which have a close link to, well, policy making and Brussels, EBA, the European Biogas Association is available here. And also ECN will be, that's the European Compost Network. They will be online, and also from their perspectives, they look at well, the development of these technologies and the implementation and so on. And we are also very happy with Greenovate as a very good dissemination communication partner. And well, it's a nice team, and we'll show you a bit more about the project itself. So our main aim to remove barriers and promote nutrient recovery and bio-based fertilizers from secondary raw materials. And then some examples: bio-waste, manure, and wastewater. But a little bit more, we'll see that in a minute. The whole project has a structure of, we start with checking out what technology are in the field right now. So we made a long list of more than 75, actually more than 150 technologies of existing installations that transform secondary materials into alternative fertilizing products. And from this very long list, we had quite a big assessment to get 25 case studies. Yesterday I heard the example of going to a shoe shop and you have 150 pairs of shoes. You have to select 25. That's very difficult, but we managed. So we have this set, and now we are analyzing actually everything and to see the whole value chain, what's in there, what are the costs, the benefits, what are the feedstocks, what is the market potential, the legal aspects, etc. And we do this and to find out and showcase then the 10 to 15 most effective technologies with a multi-criteria analysis. And we do all this together with stakeholders. We actively engage them. This is our first event, but we also already had 4 online workshops to show parts of our results and also get inputs to see to make the best out of it. Here, this is another picture of our project, more work package wise. So we collect the case studies. We have all these value chains, and we take the most typical feedstocks, then technologies, and then you have products, and then of course the application. So we really look not only at technologies, but at whole value chains. And first, the technology are analyzed in work package 3, and work package 4, the products and applications are more analyzed. And then overall, for the whole value chain, we look at the market replication potential by looking at availability of feedstocks, potential to upscale the technologies, what is the potential market, regulatory barriers and enablers. We look at costs, of course, and then we get a final market potential, taking into consideration everything what I mentioned before. And of course, we also look at social risks that can play a role in this also in the acceptance of the different products. And of course, again, a lot of events and workshops. They're also directly related to the different work packages. So we have 25 value chains. It includes bio-waste, the green waste, and also kitchen and garden waste, food waste, and that can go into compost, digested, and also digestion and composting. Of course, we look at agricultural residues, but especially also manure, which can be, you can do many things with manure. It looks here, you can have this liquid fraction, and from that fraction, you can even have 3 potential pathways. You can really have a different set of products depending on how far you go into this whole processing of the manure. You can go very far, we see. We have also some examples of hydrolysis processes, for instance, poultry feathers. Of course, struvite from wastewater, very important technology. And also we have a look at biochar and maybe also mixtures of biochar with other products to have some nutrients in it. So this is some impression of the technologies that we have. They are actually, the technologies are already in an online catalog. You can already check them on our website by using this code, or just go to the website. This is a first version. We will have many more results, so we will expand the case studies until quite complete overview of these technologies and their barriers and enablers and the pro and the cons. Well, we are in mid of this assessment, so actually it's a bit of repetition, so I go for time's sake, I go a bit quicker. Analysis for fertilizer products, it's nice that within our project we had selected 25 value chains, and then also from those selected value chains we asked to send 1 kilogram of their final product for analysis to PWR, and they do a lot of testing, and they will say more about that in the next presentations. And this is very nice because you can compare very different fertilizing products in one go, so that's for comparability very interesting. We have a regulatory analysis. Our first policy brief is already online, so please have a look. And if you have any questions, Lucille is also here. That's very good, from EBA. And we will have a full deliverable with analysis of what are the current regulatory barriers and drivers for all these 25 technologies, and then grouped together, of course, a little bit. But it will be also upcoming deliverable. We have an open forum of stakeholders, so if you're interested in general in this project, please go. You can go to the LinkedIn joint open forum. You can also send an email to us or Greenway to be signed up for the newsletter and invitations for events. Very welcome, of course. And well, we have more events to go today, of course, but also we'll have a nice event 23 of November on fertilizer products, impacts and use in Poland, in Wrocław, organized by PWR. And we will have more events to go, so please, join us. We do this together with Vertitech, as already mentioned. Very pleasant cooperation. We learn from each other. We have, of course, we do almost the same, but we have different approaches. So that's also nice to see. And happy to collaborate further with them and until the end of the project. Well, that's it. So we have, I would like to say, thank you for listening, but also we'll have many more presentations. We'll try to keep a bit of time, so please keep time. And also, if you're not sure, look at the right, you will get some notes and flags from, okay, please finish your presentation, because we want to finish really at 3, and we have a very nice round table to go. Okay, so Maria, please, then it's your turn. Yeah, thank you.
Hello, everyone. It is very nice to have all of you with us in this FertiCovery event. My name is Maria Kyriazia. I'm a senior researcher in the National Technical University of Athens at the School of Chemical Engineering. I will present you the 25 selected case studies from the FertiCovery consortium and very quickly how we arrived to these 25 technologies. Here is the road we follow in order to arrive to the scope of these projects, which is to describe and give more information about the 10 best available technologies that can be used for the biofertilizers recovery and production from waste streams. So firstly, we start with a long list. One of our KPIs is to have a list of mature systems for BBF production from waste streams with TRL higher than 7. For this, we made a first, let's say, selection. So we arrived in list and inventory with 174 technologies, and this inventory contains some main parameters. I will show you a slide about them in a few minutes, and these parameters helped us through a multi-criteria approach to select from them the 35 and then the 25 with the higher score in the criteria we implement. And finally, with this short list, we go in deeper, in more detail, in order to have our final selection of the 10 best available technologies. Here is the sources of which we find these more than 200 technologies. We use European platforms and databases. We use Horizon and lists of European projects, and not only Horizon, but also LIFE and Prima project. Also, we use some clusters like BioRefine clusters. Of course, we use contacts from the partners' portfolio. In this long list of 174 technologies, which are very shortly described in a database and in a deliverable that will be available publicly in a few months after the end of the review from the European Union and REA. In this LCI, we have in this inventory we have the technology categories, the PFCs and CMCs, the name of the products and technology, the description of the feedstock, the TRL, and the application test if there are any of these. From the long list, we went to the short list. We follow the methodology you can see in this diagram, and our colleague from Cardiff, Francisco Corona, will explain you in the next presentation. So, we finally arrived to some to the 25 technologies, and we can divide them in some categories. As you can see, the category with the most of these technologies is anaerobic digestion, is very well developed technology, and this technology can also be combined with membrane filtration, with precipitation, with composting, giving us many different final products. Of course, solid and liquid fraction of digestate, but also compost, ammonium nitrate or ammonium sulfate, and potassium salts. Then we have 4 different value chains systems that could be put in the composting group. Here we have tunnel composting, open window, and composting, and semi permeable membrane window composting. We have 4 representatives in the hydrolysis group. The input here could be digestate, sewage sludge, or keratin waste, and from this group we can take liquid organomineral fertilizer, biostimulant, and mineral concentrate. Of course, we have the membranes. Membranes is a technology that, as we saw, can be combined with anaerobic digestion also. From this technology, we can have some biostimulants, and finally, we can have in this group, in the third group of this slide, we have stripping and scrubbing representatives. Of course, the product here is ammonium nitrate or ammonium sulfate. And some, let's say, more less implemented technologies. We have slow pyrolysis of mainly of wood residues from composting technologies. So we have 3 different value chains here, and of course the final product is biochar. We have 2 technologies in the group of precipitation, of course, for struvite production, and a more innovative technology, a plasma-based technology that can convert manure and digestate into nitrogen-enriched slurry. Oops, sorry. This is from my side, so if you have any question. Okay, Francisco will continue with the selection methodology. Thank you very much.
Hello to everyone. Thank you, Maria, for the introduction. As Maria mentioned, my name is Francisco Corona. I come from Fundación Cartif, a RTD located in Valladolid, in the southern of Spain. And let me start to say thank you, Estefania, to mention OneNote project, because as a project coordinator of the project, I'm very proud that the agency take into account our project as an example of a nutrient recovery topic. So thank you very much. We tried to do our best during the last 4.5 years in order to improve the knowledge about the nutrient recovery in wastewater and brine. So thank you. And I am still here today to talk about what is the technology, the methodology that we use to pass from the long list of the technologies that Maria previous mentioned, to the shortlist. I don't know if... Yeah, but I don't know what is the problem. Okay, thank you. I start to say how it's important to focus the topic of the nutrient recovery nowadays, because as you can see in this slide, the usual value chain that we use to obtain the biofertilizers or take into account all the agri-food system is a linear, okay? It's a linear value chain. In this case, usually you carry out the extractions of the mineral resource, we produce the fertilizers, we use these fertilizers in the different, to obtain the different crops, and in many cases the problem is we don't, or we obtain, or we optimize the nutrients, the use of the nutrients in the crops, and the problem is we have loss of these nutrients that is not well used, and for example, due to leaching or other phenomena, we have emissions or loss of these nutrients, and these problems, or we obtain different environmental problems with from these emissions. So the idea is to reduce the dependence of these resources, because in many cases, for example, in the case of phosphorus is a critical raw material. So the idea is to reduce the external dependence of Europe from this finite resource. The idea is to develop a circular model, okay, the circular strategy, and change and close the loop for the value chains in order to obtain the model that we have here with the cycle, okay? In this case, we have several benefits. Obviously, we reduce the dependence of the mineral fertilizers. We close the loop for these nutrients, okay, because we take advantage to reduce, reuse, and recycling the phosphorus, nitrogen, and other important nutrients in order to incorporate again in the value chain. We have lower cost and reduce the supply risks, reduce obviously the environmental problems, and try to promote healthy practice in the soil and the sustainable production. Okay, so focusing on the development of the methodology to obtain the shortlist. What is the idea, or what is the main objective to obtain this shortlist? The idea is to identify, as previous mentioned Maria and Martin, the main objective of the project is to obtain or identify the best technology for the nutrient recovery practice, okay? So we start with the idea to identify the best technologies in a mature level, okay? So in this case, we focusing on TRL 7, 8, and 9, okay? To develop a short list in order to obtain the best technologies that we can use for this practice. So the idea is to create an inventory that contains all this information, this important and crucial information, taking into account the different case studies that we developed during the project, and how we can or we carry out all this inventory using the multi-criteria approach to identify what is the best technologies to obtain the shortlist, the 25 technologies or case studies. Thank you. And what's the starting point? The starting point is the construction of the long list, okay? This is the key points for the construction of the long list. Maria talked about in the previous intervention. We have this, or we try to screen these mature technologies. We combine the different literature review, the different European projects that we have available, the partner portfolios at different platforms or database in order to compile all these technologies that match with all the criteria that we have. Apart from that, it's necessary to standardize the inventory files. Okay. In this case, we identify different key aspects that is necessary to score, to select all these the shortlist, all these technologies for the shortlist in a multi-criteria way. And when we compile and we define all these categories, the last part is compile all this information or develop all this information and compile the information in an Excel inventory. Okay. So in this slide, we can see what is the methodology that we follow. Okay, with the definition of the shortlist. The idea is to use a funnel methodology and pass for the long list to the shortlist in a good way. So we start with the initial inventory. We have more than 150 technologies. In this case, as previously mentioned, Maria, we carry out the classification of these technologies in different groups, taking into account the process, the main process that involve in these technologies, for example, biological, chemical, physical, or others processes. The definition of the 6 indicators, these 6 indicators that is necessary to score is the feedstock availability, the technology maturity, the availability and the cost, the regulatory market and framework, the efficiency of the agronomic applicability, and the EU alignment and replicability. Sorry. Why we select these indicators? Because we need to represent or to take into account all the important pillars that is necessary to represent in the selections of the best technologies. If we need to select the most robust technology, obviously it's important to take into account the technical part, the characteristics of the agronomic products that we obtain, but obviously it's quite important to take into account the economic part and the regulatory, because if we select a technology that we obtain a bioproduct, that this bioproduct is not permitted or is not easy to use or to put in the market, they don't have sense the selection that we carry out. So it's necessary to take, and for sure, the environmental point of view. So it's necessary to to score and have a reflection and a collection of the information about the main criteria and main fields, main pillars that involve all these technologies. When we finish the quantitative scoring from 1 to 5 of these indicators, we have more or less all the information and all the material that we need to carry out the criteria analysis. The next step is to organize all the information that we, to show this information that we compile in a stakeholder workshop. Okay, why? Because we carry out the scoring of these technologies, take into account the background and the experience of all the participants in the consortia, but from our point of view, it's very important to show this criteria and this methodology for external stakeholders and external experts in order to take into account the opinion of these people. So we organized a stakeholder workshop involving different stakeholders with different profiles, researchers, final users, farmers, industry, policy actors, with the idea to have, again, a better evaluation for these technologies and have a more robust scoring for the indicators. When we finish this procedure, we contact with our sister project, with FertiTech, in order to have collect again the opinion for the experts of the sister project And in the last part, we try to harmonize and normalize all the indicators of the scoring and ranking and carry out different sensitivity analysis with different scenarios with the idea to have the most robust final shortlist technology. Yeah.
Can you,
and I think that's all, because the next one is just a brief summary, but I think is okay. This is the type of the technology. This is the key result, the distribution that we have. We have the more part of the technologies is in the tier 9, sorry. The more represented families of the technology and aerobic digestion, composting, and hydrolysis, and the kind of feedstock. And I think that's all, because I don't know what is the problem with the... This is the main conclusion and the figures that we can resume of this methodology and the selection of the technology. Thank you very much.
We would like to invite Professor Katarzyna Chonianka from PWR team to start the presentation on the final products.
Thank you very much, Maria. Yeah, here is my presentation. So, hello. Imagine a bag of fertilizers from the past. It had a chemical composition, brand name, information about application and producer, and it was enough. But then imagine a bag of fertilizer in the future. It will have a QR code, which would actually tell a whole story about this fertilizer product, from which materials it was produced, by using which processes, what is its composition, safety, information about application, all the details, all the information and claims supported by data, which can be updated online. And this is very important because we keep producing fertilizer from waste by recovering nutrients from it. And a special allegory to Martin. Waste could be compared to an old suitcase. It doesn't look nice from the outside, but we may find something interesting in it. Macronutrients, micronutrients. So the This story will be about recovery of nutrients from waste and going to digital label, because this is the information that will be voluntary and will be introduced to a fertilizer bag, just like you can see it here. But actually those fertilizers, organomineral fertilizers or biostimulants, can be produced from waste. And as you see, waste, poultry feather or manure or berry seeds, they do not look like fertilizers, but we can process them by the use of different technologies and analyze the composition, analyze the safety, and we can produce a granular form and build the trust for such product and make sure that other users will trust it. Yeah, I also have a problem with changing slides. Okay, so if you imagine a waste material, according to fertilizer product regulation, it should have CMC, the information about material category, about its functionality, whether it is fertilizer or it is liming agent or it is soil improver or plant biostimulant, and it should be compliant with the FPR regulation, and then it receives a CE mark and can be and can reach the market. And there is a huge gap between what we are doing in our labs, elaborating formulations and technology, and market readiness of the product. So why this gap is here? Because what we are making in our laboratories is not the same as it is required by the policy. So it is very good that we meet here and we discuss all the limitations, and here we should speak the same language, the researchers, the policymakers, but also waste producers and fertilizer producers, because we have the same goal to produce a product that is safe and market ready. How it looks now, it looks like that. Our research is on the right, and registered compliant product should fill all the required fields. So actually the nutrient recovery processes now is not a problem. We have the technologies, the chemistry work, we have a product with very promising functionalities. But in order to introduce it to the market, we need to fulfill several requirements. Every year in Scopus, 600 papers on fertilizer formulations and technologies appear. And according to the registration requirements, 30 to 50 data fields should be filled. But actually, averagely, in each research paper, there are 8 fields: macronutrients, micronutrients, toxic elements, and a single test. For European Commission, and we could hear it in Stefania Rocca presentation, bio-based or waste-derived fertilizers are important. We see it in a fertilizer action plan that has been introduced in May. So more bio-based products are planned. Nitrogen and phosphorus recovery from waste should be used, and nutrient recovery investments are to be made. But there are several barriers. We heard a lot about phosphorus as critical raw materials, a critical raw material, especially in Europe. Phosphate fertilizers are produced from hydroxyapatite, from phosphate rocks that are usually bones of dinosaurs. And this is a huge geopolitical problem. But alternative resource could be animal bones. from meat production, slaughterhouse waste, but also other types of waste. But here we find several limitations. And of course, those limitations are very important because we produce fertilizers that are used to make food. So it is so important for food security. So there are several challenges, several problems like nitrogen and phosphorus recovery from wastewater treatment plant. And here we should pay attention to micropollutants, for instance, and also for sanitary security. Here there are three regulatory layers. There is a digital labeling under fertilizing product regulation. So this is like a Bible to the fertilizer researchers, but also to fertilizer company. Fertilizer digital label will be voluntary since May 2027, and it will be supplementary to a physical label. But there is also digital product passport under eco-design sustainable product regulation. Fertilizers are not included in the first cycle, that is in from 25 to 2030. Here there are batteries, textile, steel. But I expect that after 2030, a fertilizer, especially waste-derived fertilizers, will be also included there. So in my opinion, we should be ready for digital fertilizer passports. So I here included a combination of fertilizer digital label and digital product passports, all the requirement about circularity, about a carbon footprint, all the requirements for waste-derived product. We submitted 10 technologies for FertiCovery 100 technologies database. So those technologies have been elaborated during the last 10 years. Of course, we didn't know how the fertilizer compliance regulations will evolve. So there are several gaps in it. Now we know the gaps, but we do not know what the future will bring. Nowadays, fertilizer digital label will have a product function category, the component material category, from which material a fertilizer was made, what function it has, whether it is fertilizer, liming agent, soil improver, plant biostimulant, or other. And what could be expected in the future? We could have 5 drawers. ABC are already included in FPR: identification, the product details, declaration, the nutrients, safety, the contaminants. Stability and audit trails will be required for SPR regulation, but also in elaboration of fertilizer products, so important is technology, feedstock, process, scale, and agronomy, trial, yield, comparator, and statistics, how it is performed on the field, especially in 2 years study. So also this should be included in the future in elaboration of new policies for fertilizers, probably in the frame of a fertilizer product passport. So we should probably, fertilizer companies should probably translate what is now in traditional paper label. Actually, fertilizer bags became too small to include all the required data. So I see that I have 1 minute left. And the digital fertilizer label actually has no limitations. We can include there all the analytical results, all the contents of macronutrients, micronutrients, toxic elements, microbial safety. And another important aspect here is that some analysis of the product determine the classification. And this has an impact. It is actually a leverage whether a product can reach the market. And let's see the situation about cadmium. If the cadmium level is 1.8 milligrams per kilogram of dry mass, it will be compliant if a product would have PFC1B category, organomineral fertilizers, because the limit here is 3. Under PFC3A, the limit is 2, and under PFC1A or 6, the limit is 1.5. It wouldn't be compliant. So if we elaborate materials that should be applied to the field, we need to have this under consideration. And now I would like to show you the results. My team, Gosia, Grzegorz, and David, will show you some examples of chemical analysis of 16 fertilizer formulations. So this is something that perhaps in the future we will see when we will scan, or a farmer will scan a digital label on fertilizer bag, so you can see the data that can be found here. Thank you very much.
Hello, my name is Małgorzata Mironiuk. No, it's not my presentation. Yes, this is correct one. So I would like to present today our results for comprehensive analysis of fertilizing product from the FertiCovery technologies. The scope of our analysis was quite broad. So we divided this analysis for 3 parts, and I will discuss the first one. I will be talking about the physicochemical analysis. After me, Grzegorz will discuss microbiological tests. And after Grzegorz, David will discuss plant studies. So if you have any question, if possible, please ask after our 3 presentation. Okay, so the objectives of our study was characterization of different products obtained from different technologies. We have 16 samples from 25 selected technology. 16 we received physically, and we tested them. We perform a physicochemical analysis followed by a composition, macro and micronutrients, a safety assessment, a leaching test, germination test, pot trial, and then final product comparison. Some of this part are finished, some of them are in progress, as you can see. The technologies were represented by different samples. We have a few technology types from anaerobic digestion, composting technologies, hydrolysis, physical processes, physicochemical processes, and thermochemical conversion. So from different technologies, we obtained many different samples. Our objectives were to evaluate how different production technologies influence the composition, nutrients availability, and quality of these bio-based fertilizers. So we perform many analyses. We have many results from this analysis, but I try to present them briefly. So we perform macronutrients analysis, micronutrients, total and soluble fraction. At the same time, we analyzed the contaminants as arsenium, cadmium, chromium, nickel, lead, mercury, burette, and perchlorides, and typical physicochemical parameters such as pH, density, and dry matter. About the methods that we used for total carbon, organic carbon, and nitrogen, we used thermoconductometric methods. Other elements was analyzed using ICP-OES methods. Also, the same methods was used for micronutrients. For soluble fraction, we applied water extraction and neutral ammonium citrate extraction. The same methods as for micronutrients were used for contaminants, for mainly heavy metals, and other physical parameters was analyzed using potentiometric methods and gravimetric and volumetric methods. We analyzed the samples in 2 replicates. We used for analysis reference materials, blank samples, and control samples, and we calibrate our spectrometers with correction of matrices effects, and we ensure fully data quality control. Our laboratory is accredited by Polish Center for Accreditation, and we are signatory ILAC MRA. So our scope of accreditation covered almost all of this analysis that we performed. So let's move on to the results. The first type of technology is anaerobic digestion, and samples from these technologies, from this technology type, were characterized by moderate concentrate of nitrogen and carbon and organic carbon. Phosphorus and potassium also were on the moderate levels. So this kind of product can be used as organic or mineral organic fertilizers. Next group, composting. The samples from this group were characterized by quite high level of carbon and organic carbon. That's why this kind of samples could be a good soil improver, not only act as a direct fertilizer, but only as a soil improver. The next technology, hydrolysis. The hydrolysis samples from hydrolysis were the most heterogeneous group of samples. Here we have a quite big nitrogen concentration, and also carbon and organic carbon concentration, and the sulfur level was also quite high. The samples can be used as a mineral organic fertilizer or as a biostimulant. From physical type of technology, we have mainly struvite type samples. That's why you can see here the high level of phosphorus and magnesium, and quite low level of organic carbon. So this kind of samples can act as a mineral fertilizer and can partially replace the standard mineral fertilizers. Next technology, ammonium salt, physicochemical type. Here we have mainly ammonium salt recovery solutions. Here you can see we have the quite high level of nitrogen and quite high level of sulfur. Yes? Okay. Thermochemical this technology is represented by biochar, so that's why here we have mainly the carbon and organic carbon at the high levels. So this kind of samples can act mainly as a soil improver. Here you can see the results from contaminants analysis. All of these contaminants met the requirements of European Union for fertilizers. So that's very good information, can be safe used. Physicochemical parameters, you can see there are some differences between the groups and also inside the groups. What is obvious, because, for example, for dry matter, we have big differences. We have solid samples and liquid samples, so we have here different content of dry matters. Most of the samples were alkaline. Only samples from hydrolysis have lower pH. So the results demonstrate that nutrient recovery technologies can deliver a safe, valuable, and agronomically effective fertilizing products, contributing to a circular and sustainable nutrient systems. Thank you very much. This is all from my side, and now I will give the floor to Grzegorz.
Okay, hello everyone, I'm Gregory and I'm from the same team from Wrocław University of Science and Technology, and as Gosia mentioned, I will continue that topic, but I will focus on microbial composition of fertilizer, which was chosen in FertiCovery project. And why that issue is so important? Because as Gosia showed on the slide, the fertilizer, bio-based fertilizer, can be a valuable source of micronutrients, organic matter, so we can provide with that the proper condition to plant growth. But on the other hand, the bio-based fertilizer can be also a source of high load of microorganisms, which can bring some benefits, but also pose some risk. So bio-based fertilizer can be beneficial, for example, for nutrient recycling, soil activity, soil fertility, but having in mind that the same bio-based fertilizer can contain some typical contaminants like Escherichia coli or Salmonella, the need of microbiological safety assessment is obvious. So for that purpose, we analyzed 16 different fertilizers, and we tried to find the answer for two research questions. The first one is about safety of that fertilizer, and the second one is about potential impact of bio-based fertilizer on soil microbial biodiversity. And just as a reminder, this 16 fertilizer was divided to 6 different categories in which we can find the products from anaerobic digestion, composting, hydrolysis, physical, physicochemical, and thermochemical processes. In our methodology, we were focused on 4 different indicators: total fungi number, total bacteria number, Escherichia coli, and Salmonella. For total fungi, total bacteria, and total coli, we used typical methods when the microorganisms were cultivating on solid medium, and for that purpose sample was extracted, then the serial dilution was made, then we put the extract on the surface of growing medium. We store the Petri dishes with medium and extract in proper condition to let microorganism grow and form a visible colony, which then was counted, and the output from that tree test is colony forming units per 1 gram or 1 milliliter of fertilizer. For Salmonella, we use just quantitative test, which give an answer if Salmonella is present or absent in our fertilizer. Okay, let's move to the results. On the slide, you can find the microbial analysis for first technology type, which is anaerobic digestion. And the first key message is that Salmonella was not detected. Escherichia coli was detected in 3 fertilizer, but the permitted limit, which is 1,000 colony forming unit per gram, was not exceeded. Total fungi number and total bacteria number differ between products. But as you can see, for one of them, we receive very low number of fungi, for others, very high. So we can say that, that fertilizer from anaerobic digestion are safe, and they can, some of them, of course, can improve soil microbial biodiversity. Next slide and next technology type. Here we have results for products derived from composting. Again, Salmonella was not detected. Escherichia coli was detected in some of the samples, but again, the permitted limit was not exceeded. Again, we obtained different results for total fungi and total bacteria, but the amount was relatively high. So again, we can say that these fertilizers are safe and can improve soil microbial biodiversity. Third type of technology, hydrolysis. Here we didn't detect Salmonella and E. coli. And as you can see, the total fungi and total bacteria is very, very low. So we can say that hydrolysis as a method of obtaining the fertilizer is very effective in context of, let's say, hygienization or sanitization of the products. Very similar trend in physical processes. Escherichia coli, Salmonella, and general bacteria was not detected. Only one sample's fungi was detected, so fertilizer obtained by physical processes are safe. But we cannot say that they improve soil microbial biodiversity, except that one. And similar trend in the fertilizer from physicochemical and thermochemical processes. They are safe because Salmonella and Escherichia coli was not detected, but total fungi and total bacteria was only observed in one sample, and only that one technology can improve soil microbial biodiversity. Okay, based on results, I prepared some conclusion. Yes, that Salmonella was not detected. Escherichia coli was detected in some samples, but the permitted levels was not exceeded. And on the other hand, we observed different number of fungi and bacteria, and it was depending from the type of technology used to obtain the fertilizer. And last slide, some recommendation that we still have to control the Salmonella and the Escherichia coli. If Escherichia coli is present, we should pay attention when we use that fertilizer, especially in edible crops. And regards soil impact assessment, this fertilizer, which contain a huge number of colony forming units, can enhance the microbial activity of soil, but we know that based on some laboratory tests, it's not possible to say if they are improved soil microbial diversity or not, but it is possible after plant tests where we're using the fertilizer, and David will describe the plant test. Thank you very much.
I have to remember to look at you sometimes. Hello, my name is Dawid Skrzypczak. I'm from Wrocław University of Science and Technology also, and we are waiting for my presentation. Okay, I'm ready. Okay, so now I'm say something about the germination test, and we conducted the germination test according to the EOC the 208 norm. We used like a substrate soil mixed with a sand to improve the structure. And we conduct our test on wheat and cucumber, but on this presentation I will focus only on the wheat due to the time. And we analyzed 16 different bio-based fertilizers, and additionally we used two additional group like a control unfertilized and one reference fertilizers, and the fertilizers were applied at the dose corresponding to 100% of nitrogen requirements for wheat and separately for cucumber. And after 14 days, we analyzed chlorophyll content, overground parts length, root ball parameters, fresh and dry mass, but also germination power, because it's very important factor according to EOCD, because we should because we should achieve for control above 80% germination power. So it's very important according to this regulation. And for the first group includes products based on anaerobic digestion, and here we received very excellent results. The best results was observed for fertilizers too. Then I wish to say which type of fertilizer that. And here we received about 21% higher fresh mass compared to the control, and about 50% higher mass to the reference, and about 50% compared to the control. In going to the stimulants, you can see that we received lower stimulants compared to the reference, but we didn't observe the statistical significance between those groups, so the results are very similar. Going to the chlorophyll and contents and root ball parameters, overall root length, surface area, root volume, we achieved the best results for fertilizers too. And here you can see the technology profile about this 4 different received fertilizers. And in summary of this group, fertilizers 1 gives good biomass and root response, but best overall response we received for fertilizers 2, where we used to produce, where the production based on anaerobic digestate, but also on composting. Going to the composting process is the next group-based products. In general, the response was more moderate than in some other groups, but differences between are visible. And here we also receive higher, in most of the bio-based fertilizers, higher fresh mass than reference, and like in the anaerobic digestion products, we also received lower stimulants than reference group, but in the same time higher to the control. And here we can't see the evident relationship with fertilizers and root ball parameters because we didn't receive the same the same effect for each of the root ball parameters. Going to the summary of the composting, the highest chlorophyll content we received for fertilizer 7, for fertilizer 8, moderate response, and for fertilizer 9, best overall root response. So this means that the type of waste and the composting system can change the agronomic value and bioavailability of different nutrients. And the third one is hydrolysis, and the hydrolysis best product showed one of the most interesting response. Here we have also one product based on savage sludge, about mentioned Professor Chojnacka. And here you can see that we received very good results from fresh biomass compared to the reference, but also in the same time very similar steam lengths according to compared to the reference group. And what's more, the best overall response we achieved for savage sludge hydrolysate. So it's very important, I think, to discuss about the regulation. And moderate and balanced response we received for fertilizer 14 and fertilizer 15 gave strong root surface and volume, but low germination power. So it's also what is very important also for agronomists. The next category is physical. Here we also received higher fresh mass for our 3 different tasted bio-based fertilizers. 1 minute? 1 minute and 10 slides. Okay. Okay, so maybe I will go to the summary of this category. Here we received very different response for each of the root parameters and other part ground parameters, and the physicochemical group contains, for example, struvites and ammonium nitrate. And here we received the best results for ammonium nitrate is the fertilizers 21, and also for root ball parameters. So it's a very important thing that we can change the mineral source for renewable sources from wastewater in that case. And we received also one product from thermochemical processes, is a biochar from wood chips. And here we received very similar results compared to the reference, but we should remember that biochar not provide directly the nutrients, but improve the soil, water retention, soil health. So we should wait a longer time to receive the better results. And to the end, I would like to say that 1 month ago we started the pot trials with different different 5 conditions: standard, drought, salinity, acidic, and alkaline. And the duration is 5 months. And after this 5 months, we will also analyze the biometric parameter, but also we will mineralize and make a full multi-elemental analysis of biomass and calculate transfer factor of nutrients in a soil plant system. And additionally, as mentioned Grzegorz, we will make a full soil health analysis. And every our results will be used to prepare the practical guidelines in 7 languages, but also I hope to prepare the policymaker recommendation according to your guidelines, which you show us. And thank you very much. And in the same time, I would like to invite you to our conference. In the meantime, you should receive the flyer with more information about our conference in November. Thank you very much. And if you have any question, we are here.
Well, thanks a lot, colleagues from PWR, for your block of presentations showing an impressive amount of results, and looking forward, of course, to the rest of the outcomes of this whole research and our use of it in our project. We are having now a next block of 3 presentations, which are from 3 real cases and their experiences with alternative fertilizers. So first of all, we have Mr. De Wilde from Datricom, and he will speak online. So he will log in here. Yes, there you are. Hey, Dennis.
Hello.
And I will ask to keep the time at 10, 12 minutes, something like that, please. Yeah, thanks a lot.
Okay. So I start from the beginning. I hope you can see the presentation. Okay, so I will start. So the nitrogen recovery, we have demonstrated this in the field. So we have the presentation will show you some use cases and some new developments we are doing. So I started this company in 2014. Always the focus on ammonia recovery. We have a patent since 2019 for this technology to remove ammonia from waste streams and produce an ammonium salt. And this we are doing in plug-and-play containerized systems. I will show you later. So this is the reason why we are doing this. We have the ammonia cycle, if you see this, in nutrient-rich regions. You have crops, you have livestock, they are eating the crops, or digesters we've seen in previous slides. And this has an output of manure and digestate. And there you have all the proteins transformed into ammonia. And the normal route is to do a biological treatment of your wastewater or your waste streams. And this will produce nitrogen gas, but you need energy. And in the next phase, you have the chemical industry using the Haber-Bosch process to produce from nitrogen gas, again, ammonia, again with energy and gas. So this is the cycle, and we are trying to close this cycle with our technology, using a lot less energy. And the best thing is that we have organic-based, bio-based ammonia. Yes, do you hear me?
Yes. We don't see your presentation in full screen mode, and it is stuck in the first slide.
Okay. Do you see it now?
Yes, but not in full screen mode.
I did full screen mode. I did start, it's in the presenting mode, so I don't know what I can do else.
Share the screen again.
I'll try. I can share it again. Maybe it will help. So I share. Do you see it now in full screen?
Not in full screen.
Okay, strange. Then I'll wait.
Otherwise,
then I will try another route. Yeah, I'm sorry for this. Yeah, I can do screen 2, for example, and then I will put this presentation there. Is this better?
Now we can't see the presentation.
Oh, here it is. No. Yes, very good. Yeah, thank you.
Okay, success. Okay, next. So you can see this this cycle I just explained to you. So this is the, I hope it was clear. So we're trying to close this loop of ammonia. So this is organic-based ammonia. This is ammonia coming from the chemical industry. And we are trying to close the loop and producing organic-based ammonia. And we're using a lot less energy than destroying it and producing it again. So this is the main reason why we are building these technologies. These are all the use cases linked with organic waste where we have active plants. So one is the landfill leachate, the digested municipal organic waste. I'll show you some examples. Then you have the piggery and the dairy farms, digested organic, agriculture organic waste, and the chicken manure. So these are the ones with solid organic wastes, where we try to, one of the main reasons why we do this is to reduce the ammonia toxicity in the digestion, because all these streams are used for biogas production. And the second thing is, especially for chicken manure, for example, there's a lot of energy in there, but the ammonia toxicity is the limiting factor. So if we reduce the ammonia toxicity, we unlock the energy potential. This is the technology based on the simple stripping and scrubbing technique. We optimized this and we added some extra features, making it more energy efficient. And this is the thing that we patented all those claims in 2019, and we are building it today. So the idea was to, you have an influent, you have a mechanical separator, you have a filter, heat recovery, and then you enter the installation, remove the CO2. This will increase the pH, and if the pH increases, we can easily remove ammonia going from the liquid to the gas phase, and then we are binding it with an acid and produce an ammonium salt. So in this way, we have a local production of bio-based fertilizers, and we reduce greenhouse gas emissions because we don't need to treat this organic waste with an activated sludge system that gives laughing gas as one of the byproducts. So this is one thing. Important also is the temperature. We are working at 60 degrees, meaning that the E. coli and the salmonella is also not in this scrubbing water or in this ammonium salt. That's something we are following and testing. This is an example of a use case in a dairy farm. So you see those are polypropylene machines that we are constructing and plug and play on the farm connected. So this is something we are building quite a lot in the Netherlands and in Spain and in Belgium. And the farmer will produce locally his own fertilizer. This is another example for Madrid, where we have the same application. So this is more for the ammonia toxicity we want to reduce in the digester, and we have around 70% reduction of ammonia, and we produce 56 tons of ammonia per year. This is another example of chicken where we treat the digestate of a digester on chicken manure. So here we have quite high ammonia concentrations, which we can easily remove. This is more into detail how this is working, but the time limit, if you have some questions, you can always send me an email for more details. So this is in Barcelona, also an example where we treat the liquid fraction of the municipal organic waste and remove the ammonia for a post-biogas treatment. And this was in the live infusion project that is ending this year. This is another one, the biggest one we've built it up till now. It's 10 cubic meters per hour. We are building an even longer one now that will have an efficiency of 60% to treat 10 cubic meters per hour. And it has the same goal. It's prevent the ammonia toxicity and produce a renewable fertilizer. But here the legislation is also quite difficult because the input is a waste stream, and this limits the applications. These are the active projects we are in today, and I would like to highlight the nutritive project because there we are demonstrating a new development, and that is the ammonium hydroxide production. So it means that we will have a pure ammonium hydroxide coming out of our system, meaning that we don't need to add a sulfuric acid or a nitric acid from a chemical plant. So the main goal of the project, it's focusing on manure treatment. So we're trying to make the Cision tool to have the most efficient and sustainable manure treatment strategy where we produce fertilizers with an added value. And so these are all the partners helping, all with a different task. But the goal that our goal in this project is this zero chemical ammonia recovery, where we will recover ammonia. We won't need any acid to neutralize. And this is based on an electrochemical process where we recycle our sulfuric acid and we extract the ammonia in the form of ammonia. I don't know if you can see this. Is the time almost done?
We can. Yeah, the time is actually almost finished. So
okay, I'm almost there. So this is so the main idea is that we can produce different end products: sulfate, nitrate, hydroxide, or solid ammonium bicarbonate. And in this, with this process, it's a part of a water purification process, but in the meantime, we produce locally bio-based fertilizers and reduce greenhouse gas emissions. So thank you for your attention. So if you want to contact us.
Yes, thanks a lot, Denise. We would also like to invite you for the round table. We would have some questions for you. Is it possible for you?
What time will it be?
It will be in about 20 minutes. Yeah.
Of course, no problem. Yes, I'm here. I will stay here in the meeting.
Thanks a lot. Thanks a lot. Well, our next presenter is Apostolia Zampugnari, closing the loop from sea to soil. And
hello. Thank you very much for the time being and the opportunity given for this presentation. My name is Apostolia Zampugnari. I'm a mechanical engineer, an inventor, and a researcher. The company I represent is called ASEA Bioenergy. And what we do is we are closing the loop from sea to soil. So what we do is that we recycle seaweed biomass, basically coming from Posidonia oceanica plant, and convert it into organic fertilizers, compost, and biossoil improvers. The problem now, we are based in Kos Island. We established in 2021. And we have noticed that more than 30 million tons of seaweed biomass was ashore each year in Mediterranean coastlines. That means that there's a high contribution in global warming and, of course, decrease in rainfalls. Also, there is the 80% of this biomass ends in landfills. And this, of course, is very costly. The waste removal costs for municipalities or businesses is very high. And another also big target or goal is the excessive use of chemical fertilizers that has been noted in Greece, and which of course is responsible for up to 80% of soil degradation and other crop health and nutrition problems. So there is an EU urgent need for circular feedstocks, and this is why we ended up with this solution, where we offer a service and a product. So what we do is we offer recycling services, coastline, in coast cleanings, etc., for municipalities, but also for hotels that they are the end users of the beach. And in the same time, we create innovative products which contain natural amino acids, high organic matter. They are peat-free, where peat is about to be banned, or at least it has some restrictions from EU in use. They are chemical-free and heavy metal-free, and also they have the ability to retain water, so we end up with also decreasing water consumption in agriculture, which is also something we need to address. So for each 1,000 tons of Posidonia biomass that we collect, we have a strong prevention of CO2 emissions. We produce 600 tons of compost and restore up to 300 hectares of degraded farmland. Our production is natural and eco-friendly. We use composting method in aerobic thermophilic fermentation, in open withdrawals, and we have a capability to produce about 4,000 to 5,000 tons per year. And this is also by collecting the 15% only of the biomass Bososor in our area, in Kos Island. Of course, we utilize as well other streams that come from winemaking factories and olive factories, as well as hotels, and be able to use them into our fermentation process. The products are unique because they improve taste, they regenerate soil, they boost plant health due to the natural amino acid content. So this is really, really strong. And I think in the questions after all, I would love to discuss further on this. And that we decrease water waste and protects from environmental stress as well. The values and impact of our company is something that it really matters to us. We divert waste from landfills. We contribute in renewable energy production. This is one of our scale-up targets as well. Of course, we support sustainable tourism and agriculture, and we contribute as well in CO2 savings. We are conformed with ISO standards for quality and environment. We have been also certified our products through the national certification body, which is DO, that they are bio-certified. And we also have a national invention diploma of the method that we use for our production. Last but not least is the biomass valorization through channels like biotech, for marine biomass or blue carbon, so-called, and also we focus in decentralized pilot plants for circular waste management at the same time, while, as I said, targeting scale up through renewable fuels or fossil displacement, or even like in producing biomethane through this type of biomass in large quantities. There are, of course, a lot of other products which we could produce from these new technologies. This could be bioplastic, biomaterials, even palm oil replacement, which is it's a big deal and a strong target as well, or other type of biogas or biofuels. Some of our partnerships is worth to mention is, first of all, we collect from Kos Port Authority, Municipal Port Authority, specific from one port in here in Kos Island, is in Mastihari. We collaborate with the regional nursery of roads and with large hotel sectors as well. It's TUI, Atlantica, and other resorts as well as the wineries, well-known wineries. One of it, I think you will visit it tomorrow anyway. The global recognition from EU, our company has been published in FameNet platform, is the EU's platform for fisheries and agriculture monitoring, as the top forest, land and agriculture project. And this is like a big achievement for only a small SME company in Kos Island, Greece. And the key barriers, just I will go, if I have time, a bit fast. Greece has more than 5,000 kilometers of coastline, which is suitable for this biomass collection. And the ASEA Bioenergy can contribute in as a natural-based solution innovator, a circular bioeconomy infrastructure provider, and a climate adaptation and environmental rights stakeholder for any EU funding program related to biomass or to waste process. Also, the key barriers, as mentioned, is that there is excessive bureaucracy, slow administrative procedures. This is something that we faced since 2021, and we are still facing, unfortunately. A limited institutional understanding, resistance to innovation, weak enforcement of environmental legislation, local governance fragmentation, and lack of coordination with local authorities, exclusion from established economic networks for innovative SMEs in island regions, and lack of support for environmentally beneficial projects. So action required for is we could call simplified procedures, so a call for simplified procedures, stronger institutional accountability, oversight on local authorities' compliance, and targeted support for green innovation in peripheral EU regions. The team, as I mentioned, I'm a mechanical engineer. We have two more co-founders, Stamatios and Mike. They are mainly deal with the on-site operations as well, engineers. And Mrs. Fenya is the agronomist and CRM manager. She's based in Athens, and also Dimitris Kourousis, who also is an agronomist, and he's dealing with the sale as a sale manager, Northern Greece as well. And last, the project is called Triple Win. This is how I call it, because we solve a severe waste problem, and this can open more pilot plants around Greece and around Mediterranean countries as well, like Italy, Spain, etc. We contribute in sustainable tourism and agriculture, and of course, the climate impact is reduced through our project. Thank you very much for your time. Thank you.
Thanks a lot for your presentation. We have one more online contribution from Irmgard Leifert. She's from Riterra, and she will showcase 2 composting technologies.
Yeah, hello to everyone. I hope you can hear me, but I have an echo in. It's all
We hear
okay?
you well. I will remove the echo soon. Yeah.
Okay. You can see the slides or?
Not yet. Yeah, but it's coming. Yeah, we see it. Perfect. Thanks.
Okay, thank you very much. Thank you very much for the invitation to this very interesting project and all the presentations was just presented. I want to go quickly to our presentation for the composting and co-fermentation technologies operated by Riterra. We are, I want to present them and give a short overview our products and marketing and also qualities. Riterra is an operating composting anaerobic digestion plant operator within the group of Romondes. We are active in Germany, but also other countries, and we are handling more or less 2 million tons of raw materials and equivalent products. We are producing biogas and have more than 35 years experience according to the quality of compost produced from biowaste. Going further, we here you see the portfolio, and also I marked it with green the 2 composting plants, Ahrensfelde and Mönchengladbach, one in the eastern part of Germany nearby Berlin, and the other one, Mönchengladbach or Wanlo, in the western part, more or less nearby Cologne. We have, when we are spoken about biowaste and the typical German organic waste from households, it is separate collected within the biobin systems. It's treated with compost anaerobic digestion. We have our compost or liquid digestate and biogas products and have our specific markets. Green waste, it is more or less commingled with bio-waste in the bio-bin system, but also collected separately from commercial or public recycling centers. And we also have green waste from the commercial activities of landscapers who bring organic waste to our facilities or to these recycling centers. Products are also compost components for growing media, for substrates, and also in a few parts also biofuels, which is used for heatings. Yes, here is a portfolio of our operating composting plants. We also have these, we call it refinement plants or growing media plants, where compost, or green waste compost, and upper weight bio-waste compost is, or in future, should replace more or less peat and other fossil-driven components for growing media. Products, the typical sectors we attached is agriculture, garden landscaping, and energy production. I think it is self-explanated. Only very shortly, I want to set the focus on the legal background. In Germany, we have a long history with bio-waste collection and bio-waste treatment, and also compost quality assurance and compost marketing, and it is based on the bio-waste ordinance. As I pointed out here in this slide, it regulates input material, sanitation requirements, application rules, and also the quality assurance exemption regarding to documentations and regarding for transferability of the material to the waste sector. Bringing our compost from bio-waste on the market, we have also complied with the German fertilizer regulation. Just in the we heard before the EU fertilizer regulation. It is a not fully harmonized regulation, as we all know. And so far, we declare our compost within the German Fertilizer Act as more or less an organic NPK fertilizer. The picture here you see Wanlo. It is a, you would say more or less an composting technology which started in the early years of the century. It is an open windrow system on an asphalted surface with trapezoidic piles, with mobile technique more or less. Here we treated 25,000 tons only of green waste, not bio-waste. Bio-waste have to be treated unclosed. Yeah, so see here more or less a Google picture how it looks like. It is more or less an technique with machinery which are available for long times and which is proven. In this site here, it is more or less showing you from red to green the delivery of the green waste. Then we have the different piles with a different stage of stability due to turning options. And also here you can see we have a stationary sieving station. It is semi-stationary insofar to make the compost cleaner, especially at the end of the process. Organization is also regulated by a bio-waste ordinance, 55 degrees, 2 weeks, 60 degrees, about 6 days, or 65 for 3 days. We have a total quality assurance system driven by BGK, and this is also relevant for the compost quality. Here you see a test document. It is from the compost sample we also sent to the laboratory of the University of Warsaw from this typical green waste compost, particle size 20 millimeters. I don't want to go in detail, but here it is a requirement from the German Bio-Waste Ordinance and the fertilizer law to declare the plant nutrients, nitrogen, phosphorus, magnesium, ammonium nitrate, the organic matter, alkaline active substances, bulky, density, water content, and so on, and naturally heavy metals as well. I missed the salmonella, but the salmonella you will find here on the testing a document as well, not detectable. Regarding, I follow with big interest the E. coli discussion. E. coli is a so-called a bacteria which can be regrowth very quickly after the hygienization process of green waste, and this is also big discussion within the EU fertilizer regulation if it should only be a key indicator for good running hygienization scheme, but it's not more or less not for stored material due to regrowth issues. Yeah, we offer our products here. Maybe the Reterra structural compost in this area I marked here, also backed material for hobby gardeners. Yeah, then the next plant, it is our co-digestion and composting plant. Just while we see the basics, the basic runs well due to the organic waste and the experiences. But here we have the new plant for 500,000 tons of bio-waste, also separate collection bio-waste from households, and also 25,000 of green waste. We have the opening in 2 years, more or less 2 years ago. Yeah, I don't want to go to all these details. It is more or less an explanation. If you're interested, you can go through these different informations about the permit, about approvals, and so on. This picture is only that you can show what kind of development and composting plant can be, or what can be done if you want to develop, and also if you want to enhance the permitted treatment for bio-waste in an area. Yeah, here are buildings. First, the construction hall was built only for the segment of the green waste composting. In the first times, there was no roof. There was only all under the direct air. And this was the first construction works. And here, this is only the area for the green waste composting. On the bottom, you see the first construction works, and for the co-digestion unit and for the tunnel composting. Yes, maybe this site might bring a little bit more clarity. Here on the bottom is only the green waste composting the windroom composting only for green waste. Under the roof, we have here the delivery for green waste. It's totally separated. Here we have the weight bridge with the delivery of the bio-waste. Then the digester. After digestion, we have the tunnel composting. We have the air cleaning here. You can't see it, but it is a brown area here. It is a biofilter for cleaning the air, also in a combination with wet cleaning and scrubbing ammonia sulfate. A lot of technique is necessary for collecting the rainfall water from the roofs and also from the ways where the wheel end loader drives in order to collect organic contaminated, more or less, water, and this is used for the composting press if there's a need for adding water. Process treatment, again, as relevant for us is 80 millimeters pre-treatment screening. This fraction is more or less the fraction with potential for biogas development. This goes to the digester, and the overscreen about 80 millimeters particle size of bio-waste, and also the green waste for structural material. And after the digestion, also the digest residue. This was combined and goes for an additional tunnel composting. Here you see the big tunnels, and for an additional about 2 weeks composting aerobic process in order to have at last a sieving component for separation. So as well heavy goods as glass and stones and films forever. Here you have to look into the delivery hall. We also have a sorting cabin in order to put foreign materials which should not be put in a bio bin, for instance, plastic bags, manually out. But we also have to see it here in the end of the process of the screening of compost material, an additional wind sifting to make the compost as clean as possible. Yeah, maybe interesting to have a very short look in how a big fermentator, a digestion unit or a fermentator is the same, looks like. We call it is a plug flow digester. Here you have the feeding of the material goes in. You have big pedals who are responsible for removing or moving the material forwards, and with a vacuum pump, you generate the solid residue, the digest, the bio waste digester, we call it. And yeah, this is you see in original for operating the pedals. The tunnels, here you see the big tunnels. We have 10 of these composting tunnels, which can be put in 500 or 400, 500 tons of composting material. Essential is that we must have an aeration system. We called it a Spigo injectors. They are on the bottom of these tunnels. Here you see it in a graphical in a graph, and there the fresh air goes through the material insofar that we have a circulation. The feeding here is charge and discharge with a wheel loader. It is also possible to make it totally, or more or less totally automatically, but here was a decision to make it the mixture as well, and as also the turnings with wheel end loaders. Exhaust air cleaning. We have, hygienization is more or less the same as I described shortly for the Wanlo plant, open windrow composting, the requirement set for the German biowaste ordinance. Maybe also here the star screener and multi-stage separator, as I mentioned shortly before, it is an supply air to distinguish and separate the light goods, the films, the heavy goods.
Hello. Thank you. Could you round up the presentation? And if possible, would also, if you have still time afterwards, we would also would like to invite you for the round table, if possible.
Yeah. Sorry, when I didn't look on the timeline. Maybe a last sentence. For us, it is very important that we produce good quality of the compost, which is certified, which is controlled by the fertilizer ordinance, and also to make advices to the farmers, to the landscapers. And this is my last slide. And with our presentation of video films for explanation, the use of compost. Thank you very much, and sorry for the timeline.
Thanks a lot, Irmgard. Yeah. So we'll now quickly set up for our roundtable, which will be chaired by Stefania Rocca from the REA. And yeah, we will like to welcome the the invited speakers to the floor.
Thank you very much. First of all, to stay over the lunch. It was great to hear all the presentations so far, and I would like also to thank the speakers. So we heard about how important is the sector strategically, environmentally, and also like about some economic benefits. And the time now has come to move to the next discussion. So what will actually take to turn all these promising solutions and outcomes that you presented into concrete, well-functioning part of the European fertilizer market. And for that, I'm delighted to have a very expert panel of speakers that will bring different perspectives to answer these questions. So first of all, I would like to introduce Chris Borovic. So he's professor at the Lukasiewicz Research Network, New Chemical Synthesis Institute in Poland. Sorry for mispronouncing. And he works on sustainable synthesis and low impact industrial technologies. Then the second speaker is Massimo Pugliese from University of Torino. He's a professor specializing in plant production, organic farming, and sustainable crop management, and also partner in FertiCovery project. Then I would like to welcome Lucille Sever, so she's policy officer at the European Biogas Association, also partner of the FertiCovery project, and she works to advance biogas and renewable biomethane as key component of Europe green transition. Then I would like also to ask back Apostolia Tsapouniari. She presented earlier her company, so she's co-founder of ASEA Bioenergy, as she explained, pioneering in the field of sustainable agriculture. I would like also to introduce Ilias Papastopoulou, and welcome, and is farmer and deputy representative of Kos locally grown, and he promotes also an initiative for local production and sustainable agri-food systems in the island of Kos. Thank you for having us and joining. And so then we also will have two speakers online that will join us online. So we have Professor Irmgard Leifert. She just presented her work on compost. And also we would like to ask back Dennis De Wild. As he mentioned, is a co-founder of Detricon company, and also responsible for the patents that he explained just before. So I would like, first of all, to ask by an opening question to Lucille and to Massimo Pugliese and to Irmgard Leifert. So it's about how we promote the transition towards a circular fertilizer market. So as we discussed in the previous session, but also in the plenary, Europe has an ambition to reduce its dependency on imported fossil-based fertilizers and in general products, and make in this area a greater use of available nutrients from waste resources and other secondary raw materials. So my question to you is, what do you consider to be the most important barriers towards the achievements of this transition? So regarding specifically circular fertilizer.
Thank you. So I think when we are talking about circular fertilizers, all the products that we've presented today, so solid, liquid digestate, struvite, mineral concentrate, potassium salts, ammonium nitrates, the challenge is clear, and it's the same for all of these products. They are still produced at small scale. They are often more expensive than mineral fertilizer, and they also face limited willingness to pay from farmers. So we really need both, I think, scale and still also policy support to make them competitive also with mineral fertilizers. And so if we really want to make this transition in general, I think we need a clear business case for all these products. And policy there can help in several ways. So first, the easy first answer is to continue to provide temporary public support to really to producers to really bridge the gap price that is existing. So by providing production subsidies, then what we can do is to try to progress towards a level playing fields filled with conventional fertilizers. And there we can have measures such as carbon pricing or taxes on mineral fertilizers, or we can also have, for instance, blended target with the recycled nutrients in fertilizers. We can also play, for instance, on increasing the farmers' willingness to pay, and this goes through improving quality standards of these products. Also recognizing all the ecosystem services that are provided by these products in comparison to, again, mineral fertilizers. And finally, what we can also work on is to reduce production and transaction costs for these products. And here, well, innovation is still very important. Working also on improving local value chain is important as well. And of course, tackling all regulatory barriers, because they end up also by being costs on producers. And I would just finish by saying that it's quite encouraging, because with the fertilizer action plan that you mentioned, many of these aspects have already been have started to be tackled a bit, so it's going in the right direction.
Thank you, indeed. Thanks, Lucille, and I'm happy that you welcome also this new initiative that indeed will tackle these barriers and will also support many of the aspects that you mentioned to bring the small scale maybe more to the take up to bigger scale. And as we said as well, so I would like to hear from Massimo Pugliese, Professor. Could you please say from your perspective what will be the main barrier towards achieving the transition to a green circular fertilizer market?
Yeah, thank you. Yeah, you can hear me now. Thank you. Thanks for this invitation. When thinking about the transition to circular fertilizers and how to reduce our dependency from mineral fertilizer and from imported fossil fuel-based fertilizers, I have in mind some barriers that at present exist from different perspectives. If we look to the policy and the regulatory barriers, I think one of the main barriers that we still have, apart from the lack into the real harmonization of the European regulation of fertilizers, one of the main barriers is still, in particular, the end of waste directive and framework. Because we know that in each country, then the interpretation of the end of waste criteria, so how to shift from a waste that is considered, can be considered really a product for a new process, can significantly be different from one country to another one. So from this point of view, I think it might be really important also to have a standardization, okay, some standards and homogeneous evaluations of this approach within the different EU member countries. Then look into the economical barriers. We know for sure that in general mineral fertilizers are cheaper compared to the circular ones, although we are assisting due to different reasons, due to recent crisis, due to war, due to the Hormuz Strait that was closed, how we can be really, let's say, susceptible to huge increase of cost if we just consider the price of urea, price of nitrogen fertilizers was just doubled until a few weeks ago, and now it's returned, let's say, to a more normal price. But even if, or even when the fertilizers price increase, like in this case, we are still having difficulties, let's say, in comparison the price of mineral towards the one from circular base. But why this? Because generally we are focusing our attention only on the nutrient content. We are not giving, in my opinion, a real value of the circular fertilizers, also in terms of other ecosystem services or environmental services that these fertilizers can provide. If you think to the organic matter, so to the carbon storage capacity and possibility when using some circular-based fertilizers, we are not thinking about, of course, the CO2 emissions, and also we're not thinking, or let's say, giving a good value, economic value, also to the aspects that are linked to the soil issue. Okay, you know that we have also not only soil emission, but we have a new law on soil that also is important if you think to the application of circular fertilizers, as well as within a One Health approach, the importance of the circular fertilizers itself in terms of regenerative agriculture, in terms of possibilities that we may achieve thanks to the use of circular fertilizers. We have some technical barriers, although I think in the last years many achievements have done, and we've seen also this morning how there are a lot of technologies. We have also some examples here in the panel, generally of able, okay, to apply this approach and to recover and convert nutrients and so on into circular fertilizers. But we still have some barriers from a technical point of view. Barriers in particular, in my opinion, from the point of view of the application of these fertilizers, application by farmers. Because we may have some fantastic products, fantastic fertilizer, but maybe not in the good, let's say, formulation to be applicable, to be applied easily by the users, by the farmers, and not taking into consideration the real needs of the farmers in terms also of providing fertilizer that can have multiple nutrients, so generally specific rates of NPK, for instance, as well as other aspects. And in general, we know that fertilizer obtained from recovery, in most cases, okay, are not, let's say, consistent. I mean, the same type of product produced along the year can have different content of nutrients because the starting material is wide variety of materials are used, because depending on the type of waste itself, the waste cannot be standardized, let's say, and consequently this is reflected into the final product. And of course, this has consequently some issue from a market point of view, because the confidence of farmers is low in general terms on the use of these recovered fertilizers, although for sure it can be improved. But for improving this, we need to provide products with a good formulation. We need to provide extension service. We need to also work on demonstration activities to show how this product can be absolutely not only, I would say, equal to mineral, but I think for sure much better than mineral, because as I said before, we're not only providing nutrients, but we are providing many other ecosystem services that mineral can't.
Thank you. Thank you, Massimo, for this broad perspective, and also for adding this new probably services and benefits that could be associated to the use of mineral fertilizers. So I would like to ask the same question online to our speaker, Irmgard Leifert. So from your perspective, what would be the most, what do you consider the most important barrier for achieving the transition towards circular fertilizer market?
Yeah, thank you very much. Just as the speakers before mentioned it well, the fertilizer action plans, there are listed 25 different approaches for bringing or creating a new market for bio-based organic CO2 low-level fertilizers. There are also some points regarding our compost from biowaste. It's typical something else, FUS, precipitated ammonia salt, or the products Mr. Bilder described. Yeah, the basic is that you have a clear quality assurance that you know, and this is also mentioned before, we have a much more variety in our composting materials. Depending on the input material, we can do something within the processes as well, but we must have a good certification. We must have a good declaration of nutrients, the plant availability, and also have good application rules for bringing it not only to agriculture, but also, as I mentioned before, as a component for growing media, for flower substrate, or whatever. Barriers, yeah, it's also mentioned in the action plan. This is animal byproduct regulation, the waste regulation according to end of waste. I showed it shortly from the German perspective. We still, even if we have treated our bio-waste through the Trappenfelde composting plant and with certifications and 12-time testing a year, we have still a waste status. Yeah, and in so far we are looking of the fertilizer regulation, the EU fertilizer regulation, but there we have hygienic rules from the animal byproduct, which said, okay, animal byproduct in the bio-waste bin due to salami, pizza, or whatever, then you must do a pasteurization. This is fully not practical and not practiced in Europe. As well, we must declare the end of waste status, even in the waste framework directive or whatever, maybe there to be legally clear. And the criteria, as I mentioned as well, E. coli, we have to also take into account. Yes, it must be safe products. We're not only regarding to heavy metals, but to the hygienization sanitation regime. We cannot use parameters which regrowth potential. What are also barriers? Yeah, from my point of view, mostly we also have to look on the financial subsidiaries within the GAP. Lucy mentioned it. The compost material, or the organic bio-waste, not only compost bio-waste materials, are more or less not listed as a kind of eco-schemes or agriculture-friendly measurements. Maybe this can only be done on the basic on strategic plans in the member states. And so far, we also promote to go forward for a recycling target, if it must be a target for mixture of bio-based CO2 generated nutrients in future, it may be. But the barriers now, from our point of view, the farmers ask for compost due to a better soil quality. And so far, yes, I would also connect, not only focus on nutrient management. The revision of the nitrate directive says a lot of calculation methods, management rules for farmers and so on. We have to take this into account. This is basic. But we should combine it with carbon farming in order that a farmer gets subsidies, even if he keep his soil healthy, to have a good soil quality. In order to, yes, now we have very high temperature. It's also for Germany, 38 degrees. It's horror, and we have to take this into account. And maybe this could be in future times to the financial support, and the financial support maybe also in the sector of growing media. When we have to replace peat, we have to look how we could create such a market, the market for replacement of peat and fossil-based materials.
Many thanks for bringing your perspective on the German situation, but also in general on the legal and regulatory related barriers. And I think that you are quite aligned with the previous panelist on giving more like legally recognized benefits for the use of recycled fertilizers. Thank you. And time now for going to the next question, which is about.
Sorry to ask, but I'd also like to add 3 barriers, if it's possible.
Yes, of course.
If it's okay, it's short. But for my side, number 1 is that if we produce bio-based fertilizers, there is still a big gap to produce, to have it seen as an organic fertilizer. So because the organic legislation says like you can only feed the soil but not the plants, and I think this is a barrier for us. I think it's better to look at it as, is the nitrogen, has it an organic source, and meaning that it's also organic and it can be used as an organic fertilizer. I think this can really help us entering in the organic market, and this will increase the value of this product. A second thing is if we can link carbon credits with the production of our fertilizer, this will also increase the value and will help the farmers or industry to produce it from their waste streams. And a third thing is more linked with the Belgium legislation for permits. One of the big issues is getting a permit, and a permit is mostly linked with the ammonia, the nitrogen emissions of an industry. And today, if you discharge, like for example, in a farm, your manure on the land, if there is less ammonia in the liquid fraction, you will also have less emissions of ammonia. But this is not taken into account. and it has a very big impact. So introducing this technology can lower the ammonia emissions of a farm, but today they only look at the stable. You see, is the stable emitting X amount of kilograms of nitrogen per animal? But you should look at, I think, a bit broader than only the stable. Those were the three remarks. Thank you for the time that I got.
Thank you, Dennis, indeed, for your valuable additional insights. And indeed, it is, I think it's very good point. And also, it is partly, or the situation will be partly improved with the new action plan to also, as you mentioned, to kind of simplify certain barriers relating to permits, but I get your point, and I'm sure the FertiCovery partners will bring this message also towards in project relating documents and recommendations. Thank you. So we go now to the next question, which is about how to go from demonstration to market deployment. And I would like to address this question to Lucy first, if you're fine. Indeed, many nutrients recovery and bio-based fertilizers technologies have already been successfully demonstrated. We heard some very good promising solutions today, but only a limited number of these promising solutions really develop into commercially viable and replicable value chains. So from your perspective of EU-funded research and innovation project, where does this development and further scale up most often fail? And what forms of supports do you think that are most urgently needed to bridge the gap between demonstration and market deployment?
So yeah, in general, there are two periods really where this technology tend to fail and where they need extra support also from policy maybe. And those are called often the valley of death. So it looks very dramatic, but it is for technologies. The first lies between demonstration really and the first commercial plant. So many technologies might have already proven themselves at pilot scale, but companies will struggle to finance that first really industrial facility that is needed to demonstrate both technical and financial viability. And basically, this is where programs such as Horizon Europe, but also Circular Bio-Based Europe joint undertaking that you mentioned earlier are really playing a crucial role, because they will support large-scale demonstration and flagship projects. And then there is the second valley, and this one is maybe even harder to cross, because once the first plant is really operating, scaling up to widespread market deployment is still very difficult. So companies will face high production costs, limited access to long-term capital, also uncertain demand, and in general also, as mentioned, fragmented regulatory frameworks. And so at this stage, unfortunately, they are already competing with the well-established mineral fertilizers companies. So they are not even yet benefiting from economy of scale. So it's really a tough period. And this is why also broader policy frameworks such as the Bioeconomy Strategy, the Circular Economy Act, the Fertilizer Action Plan, all these policies we mentioned, they are really useful to be able to work on creating demand, on harmonizing rules and all this.
Thank you very much, Lucille. And I would like now to ask the same question to Apostolia. As you said, you are co-founder of a company here in Kos. Would you like to also tell us from your perspective what is needed to go from demonstration to market deployment?
First of all, I agree with Mr. Lucida, especially in that the technologies have already proven their technical viability in many nutrient recovery and bio-based fertilizer technologies. The challenge is no longer whether these solutions work, but how to scale them into commercially sustainable value chains. So from our experience at AC Bioenergy, the transition most often fails in the period immediately after successful demonstration. Companies may have validated technologies, but they still face difficulties securing investment, obtaining permits, as before mentioned, navigating certification requirements and building market confidence among farmers and distributors. There's often a mismatch between innovation funding and commercialization needs. Research projects can successfully demonstrate technologies, yet the next stage requires significant capital for industrial deployment, working capital, market development, and regulatory compliance. So to bridge this gap, we believe Europe needs stronger de-risking instruments, including pilot-to-market financing schemes, dedicated scale-up funds, and guarantees that encourage private investment, for example. At the same time, certification and permitting procedures should become faster and more predictable, particularly for products derived from recovered nutrients and secondary raw materials. Equally important is stronger collaboration across the value chain. So waste producers, technology developers, fertilizer companies, agricultural cooperatives and farmers need to work together from the beginning, which is something that usually doesn't occur, it doesn't happen. Long-term agreements between producers and users can provide the market certainty which is necessary for investment and expansion. And we believe projects such as FertiCovery play a valuable role by generating technical evidence, demonstrating environmental benefits, and helping policymakers identify the barriers and still prevent wider market uptake. So thank you.
Thank you very much for bringing this valuable insights into the discussion. I would like also to encourage you to look at also other opportunities for scaling up, as Lucille mentioned, the joint undertaking, really looking at more higher TRL technology readiness level for certain solutions, but also this new bioeconomy investment deployment group that has been just launched, and perhaps it could be interesting opportunity for you. And now I would like to ask our online panelist, if he's there, Dennis De Wild, the same question. If still online, otherwise we can go to the next. Yeah, we can go to the next question, which is about local entrepreneurship and the development of a bio-based fertilizer company. Yeah, you just spoke to us, Apostolia, about your experience as co-founder of a small company producing very valuable products at local level. And so just if you would like to share with us what motivated you to establish this initiative and how the company has been progressing since its creation.
Yeah, ASEA Bioenergy was established with a simple objective to transform locally available organic biomass and underutilized biological resources into high-value products that support sustainable agriculture and the circular economy. The motivation came from recognizing that many biological resources are still treated as waste, despite containing valuable nutrients and organic matter that can be returned to agricultural soils. So we saw an opportunity to create both environmental and economic value by developing innovative bio-based fertilizer solutions, while also at the same time helping local communities to address environmental challenges through resource recovery and circular economy practices. Since its establishment, the company has focused on research, product development, pilot scale production, farmer engagement, and participation in European innovation initiatives. One of our most important achievements has been demonstrating that locally produced bio-based fertilizers can contribute to soil health, resource efficiency, and this is why Mr. Elias Papostolou is here, because the products already has been used. And finally, the potential we saw is came from one simple, I would love to share this, just one simple ride, you know, with our family around some landfills in Kos, and we noted we wanted to note where these landfills are and how many. You know, we were doing something like an investigation on this subject anyway, and this is where we came across this large amount of biomass. So this is when the company started, you know, in our mind, and then in you know, legally. So this is what I would love to share, and share with new entrepreneurs as well, and innovators, that they're from an idea, from a good perspective, you know, to help others as well, and not only just ourselves. I think everyone can have a winning proposal, you know.
Thank you for sharing your personal story, and also it's very inspiring, and I hope that others will follow what you are doing, which is very concrete and very important. So looking ahead, also, as we discussed today, we will have a forthcoming Circular Economy Act that aims to strengthen the single market for secondary raw materials. And this is an issue that has been discussed as well today, but also in the FertiCovery policy brief that is already available. So I would like to ask Krzysztof Borowiak, so from your, based on your experience, what are the main factors currently preventing the harmonization of quality and safety criteria for recovering fertilizing products from waste streams across member states? So what also would you consider as most important factors, and what should be taken into account in the future Circular Economy Action Plan?
So each European country has its own regulations according standardization of fertilizers.
Maybe it's not working well.
Once again. So each European country has his own regulations related to the fertilizers, and since 2019, when the new regulation covering the quality of fertilizers taken into force, the previous regulation allowed for rule of reciprocity. So mineral fertilizers will be placed on the market in one country, and automatically they were allowed to be sold in the whole European countries. Now, in the new regulation, we have different situations. So organic and organic mineral fertilizers are covered by regulation, which not allows to free placing products within countries after meeting requirements in the one country. So the problem is, I think, it has been already presented by my previous interlocutors, how to guarantee the reputable quality of fertilizers regarding the different raw materials, for example, for digestate. European regulation allows for free placing on the market products with a specific declared values of nutrients. These values are maybe varied plus minus 50% in general. So it cannot be proved in all the products. On the other hand, the nutrients are not only one factor, but however, contaminants and microorganisms may be also important in that product. So each product requires very specific certification and checking all the all the part of the sold products. On the other hand, we know that these products are not only the source of nutrients, but also, what is more important in my opinion, organic carbon. Because, for example, in Poland we have a huge problem with droughts, with not efficient fertilization because lack of water just. So organic carbon is really needed, and mineral fertilization is not enough for efficient agriculture right now. So on the other hand, we have a situation that it's an easier way to place specific organic fertilizers based on domestic regulations, because they may be less strict than European one. So there are not enough incentives to adapt harmonized regulation among the countries. Yes.
Thank you, and I take note of the certification and also the components that you are mentioning, organic carbon, as it was also mentioned by other panelists. The panelists online, would you like to add anything to this discussion? Irmgard.
Yeah, thank you very much. I could support.
We cannot hear you now, unfortunately.
It's possible?
Yes.
Okay, sorry. Yeah, I fully support what the previous speaker bring on the table. Maybe from our German point of view, we see there's also need to look on what kind or huge resources are still in the municipal waste, which is going to incineration. Yeah, more or less, the environmental agencies, I think it was 2 or 3 years ago, they made an analysis of the residual waste with about 39% of organics in, even if not all these organics, because they are packed or whatever, could be used. But there is a huge potential if we would implement a separate collection of bio-waste as one source for an organic soil improver to combine the carbon farming issue as well as I told it more or less a basic fertilization for soil and plants. We know also that we need edited nitrogen fertilizers, which are more or less efficient regarding to plant availability. But yes, and we need also a clear certification scheme for the process of the bio-based compost and other materials. We need also the control by agencies, we need a quality assurance, and we need samples that are representative for the farmers, that he is really sure what kind of nutrients amount he gets, how much stable organic carbon he can be calculate within in his crop rotation and within a carbon farming certification scheme as well. Yes, but we have to look also on resources which are just now not dumped or incinerated. And so far, yes, this is also a political issue for regulation and for implementation in the member states.
Thank you very much for these insights. And indeed, this is something that we take away from this discussion, that we need quality assurance, regulation, and a more defined action for the real implementation of the new market. And so this brings us to the final question. So we would like to hear farmer perspective and the acceptance, trust, and how to uptake these innovative solutions. So what would farmers need in order to concretely replace the mineral fertilizers or more conventional products with new fertilizing products recovered from waste?
First, thank you. And farmers, they are open to all of these new solutions. But farmers, they need to prove on the land. So to go to the land is the next step, I think. About compost and all of this we are talking here, I think farmers used it many years ago. We still use, but and I think it's the way is the only way to go to product good things. I think is the soon is come to the farm. I think the people they want to grow up things, good things. So if you need to grow up good things, you must go to the solutions.
Thank you very much for bringing us this experience. Any other panelist would like?
Sorry, I like to talk say something more.
Yeah.
Sorry about my English, but
Absolutely.
it's the first time I talk to so many people. So
very well done.
Straight from the field. Anyway, all of this is it. We use we make safe the water because the water is very important for us on this island, and on this island is not only the water, it's also the tourist. The tourism is also one big part of our problems from the farmers, and I think the water is. The recycled water is the way for the farmers.
So this is also a good potential for recovering, indeed, valuable nutrients. And I think this, with this, we can close this roundtable discussion. I would like to thank all of you for your clarity and openness to share your experience. And also, in a way, I see a big alignment. So I'm sure this is the way to go forward to the next level in the implementation of promising solutions. And I'm confident that the partners of FertiCovery will make this message very clear in the project outcomes, and we will make sure that the messages will reach the policymakers, and this can be considered in the new upcoming initiatives. Thank you, and then over to Maria and Martijn.
Thank you as well.
Yeah, thank you all. Also, thank you, Stefania, for doing the moderation for this this final interesting roundtable. Thank you all, and yeah, we keep in touch. You can always find us at the FertiCovery website, and enjoy your stay here in Kos.
Thank you.
Okay.
Thank you. We had to skip some questions,
Yeah.
but I have a lot of notes.